So we just got done talking about formal charges based on the structure that you can have different ways of drawing a series of elements. And maybe one structure is more dominant compared to the other because of electronegativities. Sometimes that's not the case. There's not a right way necessarily to draw it. If it's diatomic, well, that doesn't really matter. So oxygen is a really good example. This is how it's drawn. There's not another way typically if we draw it. You could say, well, maybe I could put more electrons on this side as compared to that side. That doesn't really work out. But there is another example where we could look at an allotrope of oxygen. An allotrope is where you have the same element and it can combine in different ways. Maybe it's 2 atoms, maybe it's 3 atoms, maybe it's 15, who knows? And it just combines. If we look at the number of electrons, we have 18 electrons that go to ozone. That's what this is here. And we can draw it 2 different ways. We can do it this way, or so 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons works. But we could also draw it, pardon my phone, we could also draw it this way. Like this, and it's really kind of looks the same. It's like a mirror image, but what's happening is these electrons are flipping back and forth, and the reality is they're kind of equally shared. Think of it as like going like the speed of light, and it is, or close to it anyways. And so what you actually have is like a bit of a bond kind of going back and forth here. So I'm not going to draw a third one, but it kind of just looks like that and get rid of that bond there. So it would kind of look more like in the middle. Another classic example of that is benzene. Each of the points in this drawing is a carbon atom. And many times it's drawn like that. It's like, well, should it be drawn like that? Or should it be drawn like that? And these guys are all just flipping. A third way, many times this is also drawn, is just to put a circle in the middle. And that shows that it is a shared bond in there. So again, these electrons are kind of just spinning in here and shared amongst there. It's not like they're found here sometimes and here other times. It's just equally shared partially all the way through. Okay, let's do a couple quick exceptions and then we'll finish up the homework problems. Some exceptions. There's always some exceptions. So that's a period. Add the number of electrons up and they may not give an even number. This is very rare, but we'll go ahead and do it. Nitrogen monoxide. Nitrogen's got 5, oxygen's got 6, 11. So as far as putting this together, if I'm not mistaken, putting them in here, 2, 4, 6, 8, 9, 2, 4, 6, 8, 10, 11. Nitrogen, or excuse me, oxygen's got 8 and nitrogen's got 7. 2, 4, 5. Or 2, 4, 6, 7. So it's not equally balanced out. And yeah, that's just how many it has. It's not an ion. There's no charge on it. And that's just the total number of electrons it has. So occasionally that happens. Also, sometimes the central atom only has 6 electrons. And again, very rare. The classic example of this one is boron trifluoride. If we draw this out, you get boron with 3 fluorides. And based on the electrons, you have 24. I'll spare you that part of the process. And this is it. Boron does not require an octet. It's satisfied just having 6. Okay, that's the end of that. Let's go ahead and take a look at our homework problems and charge through those. We're on 53. 53 asks us to write one or more appropriate Lewis structures for nitrite ion. Putting this one together, nitrogen in the center, oxygen on 2 sides, and just because we're going to do this twice, I'll go ahead and get this one set up. And as far as number of electrons, we have 5 for nitrogen, 6 each for oxygen, so 12. It's a 1 minus charge, so 1. 17, 18 electrons we have to put on here, okay? And 2 different ways I could do this. And I'll go ahead and put a double bond in there, just because I know where this is going. And the other way is to say, okay, well, I guess I'll put it over here. And I know what you're thinking. Isn't that the same thing? Yeah. You could also try putting double bonds on both sides, but based on the fact that oxygen is so electronegative, it would not allow that to happen. So given this scenario, I have 2 ways that we could draw nitrite. Now the reality again is this kind of flips back and forth, and it is shared equally on both sides of the oxygen. It's not one or the other, it's actually both. With what allotrope of oxygen is this thing isoelectronic? Remember, isoelectronic means the same number of electrons to something else. Allotrope, which we just discussed earlier, is a type of oxygen. Is it O2 or O3? O2 has 12 electrons, and O3 has 18. Therefore, it would be an allotrope of ozone for that one. What would you predict the bond lengths of NO2 relative to a single bond and a double bond? This is something we haven't talked about, but I'll kind of give you a picture idea of it. So relatively, that would be like a single bond. And a double bond, think of it as like something holding it together, because it is. So the more bonds you have in, the length between the 2 atoms becomes shorter. It's holding them on more tightly, more strongly. So 1 bond is a long bond, and 2 bonds is relatively shorter. So for this, it's like 1 1/2. If there was 3 of these and it was acting the same way, it'd be like 1 1/3. But because we have 2 atoms that's going between, it's 1 1/2. So what would you predict the bond length for NO2 relative to single or double? It'd be somewhere in between. So let's write that. In between a single and a double. It's like 1 1/2. Predict the ordering of the CO bond length in CO, CO2, and CO3. So let's look what these guys, see what they look like. In CO, we saw that earlier, it's a triple bond. In CO2, just to help you out, we'll make this go a little more quickly. It's double bonds all the way around. Double bonds. And for CO3, for that one, we'll go through some math. So we got 4 plus 18 plus 2, so 24 electrons. So we'll do one of these things. And just double check that. 18 is 4, 22, 24 electrons. Does that work out right? 8, 16, 24, but we don't have enough here. So something's wrong. I would have brought those in, it would have given us 26. Let's do this. And then we'll put our little brackets on there. There, so 8, 8, and 8, and carbon does have a full octet. So that works out. As far as bond lengths go, this is like 1.5, or excuse me, 1 1/3 for these guys. This is a double, either way you look at it, and this is a triple. So as far as bond lengths, this is the shortest. This is the 2 bond lengths, so this would be the next one, and this would be the longest because it's like 1 1/3. So they're already kind of in the right order. So short, middle, long. Okay, good place to take a break, and we'll finish up with one more lecture.